This recording is about the energy changes that accompany chemical reactions, particularly in terms of bonds breaking and bonds making. So in any reaction, we start with reactants, and the first step of most reactions is to simply break the bonds that are involved in forming the new products. And breaking bonds is always an endothermic process. It always requires input of energy. That takes us to the highest energy point in a chemical reaction. And then new bonds are made at that point, and bond making is always exothermic. It always releases energy when a bond is made. And so in the sample that is shown here, the energy of the products is lower than the energy of the reactants, and the difference between the two energy levels is enthalpy of reaction, delta H of reaction. So this overall is an exothermic process, which we'll go over again later, okay? If the energy of the product molecules was higher at the end than the reactant molecules, it would be an endothermic reaction. All reactions are accompanied by an energy change, either exothermic or endothermic. And you're probably real familiar with these graphs, but just to kind of review, again, if the energy of the products overall is higher than the energy of the reactants, so you can see if that's the case, then net, the reaction process must absorb energy, and that is an endothermic reaction. So you're looking at the net difference in the final energy of the reactants versus products. And in a similar vein, if the products end up at a lower energy than the reactants, there is energy that's released into the surroundings, and that is an exothermic reaction. So where does the reaction come from? Why are there energy changes? It's primarily breaking and making a bond. So that's what we're going to look at in the rest of this video. So just to emphasize, anytime you form bonds or make bonds, that is an exothermic process, always, 100% of the time. Some students get a little confused because biologists tend to say when you break bond, you release energy, but they're leaving out steps along the process. So this is true 100% of the time. Anytime you make a bond, that is energetically favorable, okay? Otherwise, we wouldn't make bonds wouldn't be made, right? And breaking bond, just like breaking anything, breaking a piece of wood, breaking a glass, you've got to put energy in to break something. So breaking bonds is always endothermic. All right, so there is a formula using the bond energies broken and the bond energies made to find enthalpy of reaction. And you're welcome to use that formula, but I don't really think you need that formula, as you'll see in the next couple of slides, if you keep your plus and minus signs straight. I want you to look at the relative energy consumed in a reaction with bonds being broken, and compare that relatively to the energy that is released in bonds being made. Now you can see that when you compare these two energies, that's going to tell you overall whether the reaction is endothermic and exothermic. So the wording that you might see, let's say on a quiz or exam, is at the bottom of the page, and you might want to read over that, make sure that wording makes sense to you, but that's all that's saying, is if the energy from bond making, okay, which is exothermic, if that's larger than the energy consumed from bond breaking, which is endo, okay, so if exo wins, then overall the reaction is going to be exothermic, okay? On the flip side, okay, if the bond breaking energy, which is endo, is larger than bond making, okay, which is exo, that means endo wins, and overall the reaction is going to be endothermic. All right, so here's a really simple example. look at the reaction here. And to really be careful and accurate in doing these type of calculations, it's really important to write the Lewis structure, not necessarily the lone pairs, although you kind of need to do that to figure out the total Lewis structure. But in order to really clearly see all the bonds that are being affected, it's a really good idea, and actually I always go as far as to say necessary, to write out the Lewis dot structures. So this is an overly simple example, but just to go through the process with you. All right, so bonds broken are always going to be in the reactant side, so you want to start with that. And we're going to break the hydrogen-hydrogen bond, and we're going to break the fluorine-fluorine bond, and there are no other bonds we're going to break, okay? So I'm going to look, typically you'll get a table of bond energies, so you're going to have to hunt through it on your own. Just for simplicity, I've given them to you here. Okay, so remember that bond breaking is always endothermic, and you hopefully remember that an endothermic process is designated with a positive sign. And so breaking the hydrogen-hydrogen bond requires 436 kilojoules per mole of energy. And breaking the fluorine-fluorine bond requires 155 kilojoules per mole. Okay, so collectively, bond breaking requires 691 kilojoules per mole. And so now we're going to look at bond making. So the only bond we've made is hydrogen-fluorine bond. Making any bond is an exothermic process, and we designate exothermic processes with a negative sign. Okay. Now you have to pay attention to the coefficients in the balanced reaction. There are actually 2 hydrogen-fluorine bonds that are made. Okay, so the total energy that is released from making these bonds is 1134. Don't forget your minus sign. That's probably the easiest place to make mistakes are the signs. All right, so I'm getting sloppy here. So once you have the signs right for the bonds being made, and what did I do with it here? The bonds being broken, just combine them. Just add them together, okay? So we have minus 1134 plus 691. Let me do my mental math real quick. Okay, and so the net result is minus 443 kilojoules per mole. That minus sign tells us that overall delta H of reaction is minus 443, and it's exothermic. Okay, so that's a really easy example. They can get quite tricky, so I strongly encourage you to do some practice problems and make sure you pick ones with structures that require you to draw Lewis dot structures out. All right, I want to mention combustion reactions in particular because they're very common examples. They are always exothermic, okay? Always exothermic. That's why burning things keeps you warm. And so just kind of a reminder how to recognize them, or if you're asked to draw out a balanced combustion reaction of some substance. Oxygen, molecular oxygen, is always one of the reactants, and assuming it's complete combustion, the products are always carbon dioxide and water. So let's take a minute and imagine that we were asked, what is the delta H of reaction for burning of octane, which is an additive to gasoline? Alrighty, so the first thing that you want to do in any reaction is make sure that it's balanced. And combustion, I always tell my students, balance the elements in alphabetical order, CHO. Okay, carbon first, then hydrogen, then oxygen. All right, so to balance the carbon, I'm going to put an 8 in front of carbon dioxide. To balance the hydrogen, I'm going to put a 9 in front of H2O. Now the part that gets tricky is balancing oxygen. Make sure you count the oxygen in both sources in the product. So there's 16 from carbon dioxide, another 9 from water. So there are 25 oxygen atoms on the product side. How do you get 25 from O2? Well, this is the case where some people just redo the whole balancing act with a 2 in front of the CH18, which forces you to get an even number over here. So let's try that. Okay, so I will just erase what I had, and we'll start over with a 2. Alrighty, so now I have 16 carbons. So I'm going to put a 16 here in front of CO2. And I have 2 times 18 or 36 hydrogens. So I'm going to go ahead and put 18 here for hydrogen. 18 times 2 is 36. And now I'm going to recount the number of oxygen on the product side. So I have 32 from carbon dioxide, another 18 from water. So I now have 50 oxygen atoms on the product side. So now that's an even number. I can put a 25 in front of molecular oxygen, and I'm all balanced. All right, so now if you were asked to find the delta H using bond energies, I'm not going to actually do the actual math, but I want to show you or ask you, would you know just by looking at C8, H18, how many bonds and what type of bonds you have to break there? You might easily be able to predict, okay, there's 18 carbon hydrogen bonds. So I'm going to draw that out, the Lewis structure. Okay, so you can see either from the condensed formula or from the structural formula that there are, in fact, 18, which is why octane gives such a boost to our gasoline energy. All right, so there are, in fact, 18 carbon-hydrogen bonds that are broken. So you would 18 times whatever the bond energy is for carbon-hydrogen. But I do want to point out you have got to pay attention to the coefficients. So actually, there are 36 carbon-hydrogen bonds broken. Okay, they're 18 per molecule, but there are 2 molecules. Okay, so what throws some students off is if I were to ask you how many carbon-carbon bonds are broken. It is not 8, okay, that may be tempting, so I want you to look here. There are actually 1, 2, 3, 4, 5, 6, 7 carbon bonds within each molecule. And again, take the 2 into account, so there are actually 14 carbon-carbon bonds that are broken. Okay, so just one more example, or a couple more examples of where you have to be careful. If you didn't draw the structure, didn't know the structure for molecular oxygen, you might look on the table of bond energies and just pick an oxygen-oxygen bond, which would be wrong. Because if you draw out the Lewis structure for molecular oxygen, it has a double bond. So that is a oxygen-oxygen double bond that is broken. Same thing with carbon dioxide. If you draw out the Lewis structure, you see that you don't have 2 regular carbon-oxygen bonds, you have 2 double carbon-oxygen double bonds that are broken. All right, so it is important to draw out all these Lewis structures, and I would strongly encourage practicing a few of those. Alrighty, this is just a side note. This is not something that's critical for you to know, but I just think it's interesting. Okay, as you can imagine, these carbon-oxygen double bonds are very strong. It takes a lot of energy to break them. And that's one of the reasons that we have so much trouble with carbon dioxide is it's so stable that once it forms, and it's a product from all combustion of hydrocarbons, it just kind of hangs around because it's so stable. So if it were a molecule with weaker bonds, it might dissipate more readily like a lot of the other byproducts do. And of course, that's one of the bad players in global warming, so we don't really want it to hang around like it does. All right, and just to kind of tie, since we're talking about combustion anyway, combustion reactions are always redox reactions, okay? All right, so now let's work on some actual more typical, not quite as easy, delta H problems using bond energies. This is a typical chart you might be given, so you kind of have to hunt and pick the correct bond energies. So notice there are bond energy for carbon-carbon single bond is there, carbon-carbon double bond, and carbon-carbon triple bond. So you have to be very careful to be accurate. So the general steps are always make sure the reaction is balanced and then draw the Lewis structure and calculate delta H. So let's go ahead and balance this first. I'm going to put a 4 in front of carbon dioxide. I have 10 hydrogens, so I'll put a 5 here. And of course, it's one of those tricky ones. 8 oxygen plus 5 more is going to give me an odd number. So I'm going to do the little trick where I start over with a 2 in front of the hydrocarbon. Okay, so I'm just going to put a 2 there and start over. So now I have 8 carbon and I have 20 hydrogen. 10 times 2 is 20. Now I have 16 oxygen from CO2 and another 10 from water. So I have an even number of oxygen now, 26. So I can put a 13 there. Alrighty, so now let's get bond energies. I'm going to start out by drawing all of the Lewis structures. So here is butane. And I have 10 times 2 carbon-hydrogen bonds. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I have 2. So I have 20 carbon-hydrogen bonds, and I'm going to go over to this chart, and I see that a carbon-hydrogen bond is 413 kilojoules, so I'm going to multiply that number by 20, and if my mental math is right, going to get this many. Now that is breaking a bond, so I know that it's positive. It's endothermic. What other bonds do I have to break? Well, let's see. Let me get a different color here. I have to break 1, 2, 3 carbon-carbon bonds. So, oops, forgot to multiply by the 2, the coefficient. There's so many ways to make silly mistakes here. So now I have 6 carbon-carbon bonds. So I'm going to look for the energy for carbon-carbon single bond, 348. So 348 times 6. Let's see if I can do my mental math again. Okay, so there we go. The carbon-carbon breakage is going to cost that much. And now we have oxygen. Oxygen, if you know the Lewis structure or memorize it, is a double bond. And I have 13 of those. Okay, so looking at the chart, oxygen, double bond, is 495. So 13 times 495, and that exceeds my mental math, so I have to get my calculator. Alrighty, so the total energy required to break all 13 of those oxygen double bonds, 6435 kilojoules per mole. And these all have plus signs. So I'm going to go ahead and add together all of the bonds broken energy and see what I have. So let's see, I've got 8260 for the carbon-hydrogen, 2088 for the carbon-carbon, and 6435 for the oxygen. 18. Okay, so I think that is what we have. 16,783 with a plus sign. Those are bonds broken. And now I've got to do the same thing with the bonds made. Let's switch colors again. Let's do blue. All right, so carbon dioxide, Lewis structure looks like this. So you can see that I need to make, I should probably use a different symbol for making, 2 carbon-oxygen double bonds, but then I'm going to go back and look at the coefficient. There are 8. So 2 times 8 is 16 of those, all right? So let's look for the energy for carbon-oxygen double bond. Some of these charts actually have a specific energy for carbon dioxide double bonds at the bottom of the chart, so just be aware of that. This one is not. So the carbon-oxygen double bonds and carbon dioxide are a little bit stronger than just a normal carbon-oxygen double bond. So anyway, 16 total carbon-oxygen double bonds times 799. So the energy released in making all those carbon-oxygen double bonds is, I'm going to put our minus there, 12,784. It's a lot of energy released. And then we're going to make oxygen-hydrogen bonds. So if you draw out water, you can see every water molecule has 2 oxygen-hydrogen bonds. And then we have 10 water molecules. So 10 times 2, we've got 20 hydrogen, oxygen, single bonds that we're making. So let's find that energy on the chart. And so we're going to multiply 20 times 463. And that is going to be 9,260 with the negative sign again. Now I'm going to add the 2 energies that are released upon making the bonds. And when I add those together, if my mental math is right again, 22,000, make sure you put that negative sign there. There's a lot of energy released. All right. Finally, when you're done with all the individual bonds broken and bonds made, you want to add together with the correct signs these 2 values. Now, this is why I say you don't need that formula. As long as you have used the right signs for bonds breaking and bonds being made, just combine them mathematically. You don't need a formula. So if we combine now 22,044 minus, okay, and then we're going to add to that the 16,783. The net enthalpy of reaction is going to be minus 5,261 kilojoules per mole. And that's what we expect. I mean, this is kind of a basic check, but you know combustion reactions are always exothermic. So if you don't get a negative sign when you do this calculation for combustion reaction, you know you have a math error someplace. This one is fairly easy, but there's a slight little trick. Make sure you draw the Lewis dot structures for them. And I suggest turning off the video, trying to work it yourself, and then turn it back on, and I'll go through it with you. Okay, always check for the reaction being balanced. This one is in fact balanced okay. So I'm going to draw out the Lewis structure. I want to walk you through drawing the Lewis structure for C2H4, which is called ethene, just in case you've gotten rusty on them. So you always want to start a Lewis structure by counting the total number of valence electrons. Carbon has 4, and there are 2 carbon. Each hydrogen has 1 valence electron, and there are 4 of them. So we have a total of 12 valence electrons that we need to place in a Lewis structure. You always start a Lewis structure by drawing single bonds between all the atoms. Okay, now we've used all the atoms up, and how many valence electrons have we used in this structure? Each bond has 2 electrons, so 2, 4, 6, 8, 10. So we need to place 2 more valence electrons. In addition to that, notice that carbon does not have an octet. Okay, each carbon has 2, 4, 6 valence electrons around it. So by putting a double bond in between the 2 carbons, we've now used all 12 valence electrons, and each carbon now has an octet, which is much more stable. So that is the structure of C2H4. Hydrogen is simply a single bond. C2H6, if you go through the same process here, so it'd be 8 valence plus 6 more. So now we have 14 valence electrons. And if you make single bonds with everything, you notice that you nice and neatly use up all 14 electrons. Okay, so the product is all single bonds. Alrighty, so now you look at the bond energies, and what I like to do is I like to simply make a table, and on the left I have bonds broken. That's from the reactants. On the right I put bonds made, keeping in mind that all of the numbers in the bonds made are going to be negative and all of them on bonds broken will be positive. I have 1 carbon-carbon double bond, which must be broken, and the energy of that is 611 kilojoules per mole. And I have to break 1, 2, 3, 4 carbon-hydrogen bonds. And that is 414 for each of them. There are 4. 1656, these are all positive. And then finally, I need to break 1 hydrogen-hydrogen bond, and that is 436. So I'm going to add those 3 values together. I should have lined them up a little better. All right, let's see if I can do this. Okay, hopefully that is correct. 2,703 kilojoules per mole is the energy that has to be taken in to break all those. Let's go ahead now and look at the bonds made. I am making 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds. So that's 6 times 414, which equals, it's a lot of energy released. And I've got to make 1 carbon-carbon single bond, and that is 347, negative sign. All right, I'm going to add the energies released with making the new bonds, and when doing so, I get minus 2831. Kind of close. So now combine these, making sure your signs are correct. I have minus 2831 plus 2703. And the difference between those, minus 128 kilojoules per mole. Alrighty. We are almost done. Just a couple of relationships that I want you to notice when you look at bond energies versus the type of bond and bond length. And I think to pull this out more carefully, I am going to have you look at a carbon-carbon single bond compared to a double bond compared to a triple bond. So what's happening to the bond length as you go up in the number of bonds between 2 atoms? The bond length decreases. Okay, so we're going to make a statement. As bond length decreases, And by the way, what's making it decrease? Why is the bond getting shorter and shorter as you add more bonds? You have to remember what a bond is. A bond is a strong electrostatic attraction between two atoms. And so if you're adding bonds, you're adding more attraction between these two, more and more attraction. And what happens when two things are more and more attracted to each other? They get closer together. So the closer together they get, the shorter the bond length. So in other words, the shorter the bond length, the more attracted they are to each other. All right, so as bond length decreases, what happens to bond energy? So again, let's go from single to double to triple and look at energy. Energy's going up. So let's finish this sentence. As bond length decreases, bond energy increases. Makes sense, right? If they're getting more and more attracted to each other, it's going to be harder and harder to break the bond between them, right? The stronger the attraction, the harder it is to break the bond. So this question is phrased the opposite. Just get real familiar with the concept. As a bond gets longer, what does that mean? That means they're getting farther away from each other, which means the attraction is weaker. Okay? So if the attraction's weaker, that's a weaker bond. It's going to be easier to break. Alrighty. Okay, so again, we kind of went over this already, but just to make sure, multiple bonds, so that means double or triple bonds, right? So double or triple bonds are stronger for sure than single bonds. So as a summary, the shorter the bond, the stronger it is, okay? And multiple bonds, double and triple bonds are also stronger. One last slide. There are more than one way to calculate enthalpy of reaction, okay? We've done it in the past with calorimetry. I call it the QMCAT equation. Okay, we're in a calorimeter where we measure heat. We need to know the mass of of the solution of the reaction that's being measured, the specific heat capacity, and then we stick a thermometer and measure the temperature change during the reaction. We can do it that way. We can actually do it with Hess's law. There are a number of different ways that you can get delta H of reaction. Okay, and this is what this video focused on, is bonds broken and bonds made. All right, that is it for this video.